All right, so let's go over our topic of ionic bonding, right? So before we start, we need to know what our ions are. So in the atomic structure, what we know is that the number of protons and the number of electrons are always going to be equal to each other. Hmm? That's what we have studied in the atomic structure, that you have your nucleus, which has protons in it and neutrons in it, and that is surrounded by your electrons. So, for example, if you talk about hydrogen, hydrogen has one proton and one electron. Just like that, helium has two protons, two neutrons. So since the number of protons are two, so the number of electrons will also be two. So that is a normal atomic structure. And in this situation, you generally don't have any charges. There's going to be no charge present at all on the atom because the number of protons and number of electrons are equal to each other. Now, what if that does not happen? What if, for example, if you're looking at hydrogen, so hydrogen has one proton and it has one electron. What if hydrogen ends up losing that electron? For example, it was taking part in a reaction and it ends up losing that electron. So what will happen? Okay. So we know protons have a positive charge and we know electrons have a negative charge. So your proton has a positive charge, electron has a negative charge. Let's take the example of a hydrogen. In a normal hydrogen, you will have one proton and one electron. That one proton will give you plus one charge. The electron will give you a minus one charge. So the total charge becomes zero. Now, what happens if you lose that electron? If you lose that electron, the proton gives you a plus one charge, and there is no electron to counter it. There is no electron to neutralize it. So the charge on the atom becomes plus one. Plus one meaning that it has more proton than electron. It has one more proton than electron. Now, this is an ion. Or let's take the example of chlorine, right? So when you are talking about your chlorine, in chlorine, if you have 17 protons, you will have 17 electrons as well, right? Now, what happens if that chlorine manages to get an extra electron? It takes part in a reaction and it ends up getting an extra electron. So in a normal atom of chlorine, you will have 17 protons and 17 electrons. In a normal atom, the charge will be plus 17 minus 17, which will come up to be 0. So a normal atom of chlorine will not have any charge on it. But what if that chlorine ends up getting an electron from somewhere, or it ends up gaining an electron from somewhere? You still have 17 protons. Number of protons do not change because they're in the nucleus. Now you have 18 electrons because you have gained an electron from somewhere. So 17 proton will give you a charge of plus 17. Electrons will give you a charge of minus 18. So the total charge is going to become minus 1. So you will say chlorine has a charge of minus 1, meaning that it has one more electron than proton. Is this making sense?
Yes.
So this is what an ion is. So first of all, what is ionic bonding? Ionic bonding, if I were to define it, the definition you will say is it's the electrostatic force of attraction between a positively charged ion and a negatively charged ion. So you have a positive ion and you have a negative ion. Now, what is going to happen is that you know that opposite charges are going to attract each other. They're always going to be attracted towards each other. So your positive ion and your negative ion are going to be attracted towards each other, and the electrostatic force of attraction between those two is your ionic bonding. So between the positive and the negative charge, you have a strong force of attraction, and that force of attraction is your ionic bond. Now, how does this actually ionic bond take place? To explain this, we need to understand that every atom wants to have 8 electrons in the outer shell, right? Every atom wants that in the outer shell, I have 8 electrons. Now, let's take the example of sodium and chlorine. Sodium okay, so if you want to know how many electrons are in the outer shell, just look at the group number on the periodic table. So for example, sodium is in group number 1, so it has 1 electron in the outer shell. Chlorine is in group number 7, it has 7 electrons in the outer shell. So Sodium has 1 electron in the outer shell and fluorine has 7. Both of them want to have 8 electrons in the outer shell. They don't want to have less than 8. They want to have 8. Now, what can happen is that the sodium, since the sodium is, so chlorine only needs to have one more. If chlorine can get that one more electron, it can have 8 electrons. It already has 7, it just needs one more. It gets that one more electron, it will have 8 electrons. It's going to be happy. It's going to be like, yeah, I have a complete outer shell. So what's going to happen? Sodium will end up giving its electron to chlorine. So chlorine will end up getting that electron with sodium. Chlorine will get 8 electrons in the outer shell. And as a result, it will get a negative charge because now the number of electrons are greater than the number of protons. Sodium ends up getting a negative charge and it's going to be like, I have 8 electrons in my outer shell. I am now happy. Sodium, on the other hand, so it has lost this electron. This electron is gone. It gave it to chlorine. It said, chlorine, you go ahead and take this electron. So what is going to happen? This third shell is now gone. So who is the outermost shell now? The second shell. Shell number 2 is now the outermost shell. Shell number 3 is no longer there because the electron that was there is now gone. The electron was given to chlorine. Chlorine took that electron from sodium. So now the outermost shell is shell number 2. Shell number 2 already has 8 electrons present inside of it. So sodium is also happy. It's like, I also have 8 electrons in my outer shell. And since sodium now has more protons than electrons, it gave up an electron. So now the number of protons are more than electrons, sodium will end up being a positive charge. And since chlorine is negative, sodium is positive, they're opposite charges. So they will end up with a force of attraction between them, and that will create your ionic bond. Is this all making sense?
Yes.
Okay, so this is what your ionic bonding actually is. Now, the positive ion, we always call it the cation, and the negative ion is anion. You and I already know that from the topic of electrons, right? Let's take a couple of other examples. Let's take, for example, talk about magnesium oxide. Now, if I ask you to go ahead and draw the diagram for magnesium oxide, how is that going to look? Okay, oftentimes when you're doing your past papers, they say just draw the outer electron. You don't have to worry about the entire structure. Just draw the outer shell. So we will practice with the outer shell. Now, magnesium is in group number 2. Automatically, you and I know what? That magnesium will have 2 electrons in the outer shell. You have oxygen. Oxygen is going to have how many? Oxygen is in group number 6. So it's going to have 6 electrons in the outer shell. Now, when the ionic bond is going to form, what is going to happen?
Magnesium is going to give up the 2
Exactly. Magnesium is going to give up its 2 electrons. So the electrons that it is losing is from the outermost shell, right? So magnesium, for example, if it has 3 shells, then shell number 3 will be gone. Shell number 2 will still be there. So you're going to have the 8 electrons in shell number 2. And when you talk about oxygen, oxygen is going to end up gaining those 2 electrons. So this is going to end up with a charge of +2. Magnesium would get a charge of +2. Why? Because it lost 2 electrons. So now it has 2 more protons than electrons. Oxygen, on the other hand, will get a charge of -2 because it gained 2 electrons. So now it has 2 more electrons than magnesium. So that is what your dot and cross diagram is going to look like. Let's take a look at some other example. For example, this is your aluminium, right? So if aluminium is making a bond, aluminium will lose 3 electrons because aluminium has 3 electrons in the outer shell. You talk about your nitrogen. Nitrogen has 5 electrons in the outer shell, so it needs 3 more to become stable. So it's going to end up gaining 3 electrons. So that is how you're going to figure out. You need a total of 8. If they have, they're in group 1, 2, or 3, they lose electrons. If they are in group 5, 6, 7, they normally gain electrons. And ionic bond is between a metal and a non-metal, always. Okay. So if we go ahead and we look into it. So this is the charges. Group number 1 will always have a charge of +1. Group number 2 has a charge of +2. Group number 3 has a charge of +3. So if you ever had trouble figuring out what the charges are going to be for bonding or just for any chemical equation, always look at what group they are in. Okay, so group 1, 2, 3, they are going to have same charges as the group. Group will be +1, group 2 will be 2 plus, and group 3 will be 3 plus. And then 4, you generally, they do not make ionic compound. 5, 6, 7, 5 is going to be 3 minus, 6 is going to be 2 minus, and 7 is going to be 1 minus. So you can just learn this and it will make it easy for you when you're in your exams, because all you have to do is look at the periodic table and you have an idea of what charge is present on it. Now, there are certain other ions that you need to learn about as well. So when you talk about transition elements, right, or you talk about transition metals generally, they have a, a variable oxidation state. That's the term we use for it, that they have variable oxidation state. What is oxidation state? The charge. That is it. Whatever the charge is on it, that is what we call oxidation state. Now, variable meaning that it's changing. It's not fixed. This I told you, group 1, 2, 3, it's fixed. Group 1 will always have a charge of +1. It's a fixed thing. But when you talk about transition elements, it's not fixed at all. They can have +2, +3, or whatever charge is there, they can have any of the charges. That is why in transition elements, we always write down in brackets. So for example, if it is lead 2 oxide, that automatically tells you that the lead in this compound is +2. Or copper 3 sulfate automatically tells you that the iron inside this, copper 2 sulfate, the copper is +2. Or iron 3 chloride will automatically tell you that the iron in this compound has a charge of +3. So this, for the transition elements, you don't need to worry about what the charge is going to be. It will be given to you in the name of the compound. They will let you know what the charge is going to be. But there are certain transition elements who have fixed charges. For example, zinc and silver. Zinc is a transition element, but it has a charge of +2. And silver is a transition element, it has a charge of +1. Hydrogen always has a charge of +1, and ammonium also always has a charge of +1. So you can go ahead and just learn this table to make it easy in the exam. So you just remember what the charge is and you can quickly go ahead with it. In the negative one, you need to know all 4 of these. Nitrate is always -1. The formula of nitrate is NO3. It always has a charge of -1. Hydroxide has a charge of -1 as well. Carbonate, the formula for carbonate is CO3 and it has a charge of 2 minus. And sulfate has a charge of 2 minus as well. So you go ahead and learn this table. So in exams, you automatically remember what the charge is and you don't have to worry about figuring it out. Now, when we talk about our structures, so we have our ionic structures, our giant ionic structures. And when we are talking about our ionic structure, what is it actually, right? So you have your ionic bonding, which is between a positive ion and a negative ion. Now, what happens is that these ions tend to arrange themselves in a regular manner. What do I mean by that? They will always try to arrange themselves alternatively. They will always make it so that positive is next to negative and negative is next to positive. So when they're trying to do that, when they're trying to put positive next to negative and negative next to positive, they end up making a very regular shape. Regular meaning that they will have an order. Positive, negative, positive, negative. They will have a fixed, regular order shape. It's not going to be random arrangement. Everything is going to have an order, and the atoms are going to, or ions are going to have a, a proper order, regular shape. So the shape that the ionic compounds made, we call them lattices. We say that they are crystal lattices. Lattice simply meaning that it has a regular structure where all of them have their own fixed position and they will have a proper arrangement of positive, negative, positive, negative. So arrangement is proper. They're all going to be closely packed with each other, like they're all going to be fixed next to each other, and they are going to have really strong bonding between them because it's an ionic bond. So ionic bond is pretty strong. So it is going to have a really strong bonding between them, and it is generally going to be literally ions that are packed against one another. So the a giant ionic structure, we call it a crystal lattice. That's the term we use for it. And the arrangement that you will explain is that it's going to have an orderly, regular arrangement, but everyone is going to be in their fixed position. And giant ionic structures are usually solids. This is why, because they have the strong ionic bond between them and they're closely packed with each other. The ions are not free to move. That is why they can only vibrate about their fixed position. They can only vibrate in their fixed position. That is it. When we talk about properties, right? When we talk about properties of it, when we talk about properties, so first of all, ionic compounds generally have high melting points and high boiling points. Why? Why do they have high melting and boiling points? The reason they have high melting and boiling points is because they have ionic bonding. It's because you have a positive and a negative ion bonded to each other. So because they're oppositely charged ions that are bonded to each other, they will have a really strong force of attraction between them, right? Because they're opposite ions. Opposite ions will have strong force of attraction between them. And since they're going to have strong force of attraction, you need to provide a lot of energy. You need to give a lot of heat energy to be able to break that bond. That is why ionic compounds have high melting points and boiling points. Ionic compounds are crystalline. I don't need to explain. We already know that they are crystalline. Why? Because all of the ions are arranged in a orderly manner. All of them have a regular arrangement where they are fixed in their position. And so another property of ionic compounds is that they tend to be brittle. What do we mean by brittle? Brittle means that they break very easily. Why? Why is it that ionic compounds break very easily? Let's say you have an ionic compound with you, sodium chloride. Sodium chloride is salt, right? You have salt with you. You have a big cube of salt. It's all stuck together. You take a hammer and you hit on it. Now, when you hit on it, what's going to happen? You have layers, right? So this is one layer. So you can see, look at the arrangement: positive, negative, positive, negative, positive. So for example, if you look at this positive ion, it is only surrounded by negative ions. That is why you have attractive forces, because one positive ion is only surrounded by negative ions, or one negative ion will only be surrounded by positive ions. So what will happen is that when you are going to apply force, when you're going to hit it with a hammer, the layers are going to slide. When the layers are going to slide, what will happen? So right now, negative is on top of positive. Now let's say I hit it and the layers slide. When the layers slide, what happens? Negative comes on top of negative, positive comes on top of positive. The attractive forces change into repulsive forces. The attractive forces change into repulsion. The charges will start to repel each other because now you have similar charges, negative on top of negative. Now that is not what we want. Now they're going to repel each other. Since they're going to repel each other, the layers will literally split apart. They will move away from each other, they will split apart, and your compound is going to break into two. That is why your ionic compounds are brittle. Is this making sense?
Yes.
Anything you want to ask so far?
No.
Okay. Now, other properties of ionic substances are soluble in water, so you can dissolve them in water. And ionic compounds are insoluble in organic solvents. Organic solvents are your organic compounds. We have a whole topic of organic compounds coming up in the future. So organic compounds, for example, your alcohols are organic compounds. So you can't dissolve ionic compounds in alcohols, but you can dissolve ionic compounds in water. And when we are talking about our ionic bond, so the strength of the ionic bond, how strong the ionic bond is going to be, how are you going to decide that? So the strength of the ionic bond depends upon, it depends upon the size of the atom and it depends upon the charge. Let's take an example of sodium chloride and let's take the example of magnesium oxide. Now, what happens is that Sodium has a charge of +1, chlorine has a charge of -1. Magnesium has a charge of +2, and your oxygen has a charge of -2. First of all, magnesium oxide, both the atoms have higher charges. Both of them have high charges. So since they have high charges, that means that the ionic bonding between them will be stronger, which makes sense, right? Because what is ionic bonding? It is the attraction between positive and negative charge. Now, greater the charge, the stronger that attraction will be. The greater the charges, the stronger they will pull each other, right? If you go to your something you might have studied in physics, where you have studied the topic, for example, of static electricity or anything like that. So, greater the charge, greater the amount of charge that is present, the stronger it is going to pull each other. So, the same thing, it depends upon the charge. So, for example, bonding in magnesium oxide will be stronger than sodium chloride because magnesium oxide has stronger charges compared to sodium chloride. And it also depends upon the size of the atom. Think of it this way: if you have really big atoms, right? If you have really big atoms, so the distance between them is going to be greater. Since the distance between them is going to be greater, their bond uh, is going to be weaker as compared to it's an ionic compound. As compared to two small atoms. If the size of the atom or the size of the ion is small, then the bond between them is going to be stronger because they can be closer to each other. So that is the two things that your strength of the ionic bond is going to depend upon. Any confusion?
No, so just let me get something clear. So the
Mhm.
greater the charge, the stronger the attraction.
Exactly.
The smaller the size, the stronger the attraction.
Yeah, exactly.
Okay.
Now, finally, we need to talk about electrical conductivity. Okay, can you tell me what you should know this? What do you know about the electrical conductivity of ionic compounds?
They're not really hold on. They don't conduct electricity unless they're molten or in a solution.
Exactly, or in a solution. Exactly. We did this in electrolysis. So electrolysis where we were separating ionic compounds by passage of electricity, right? So ionic compounds will not conduct electricity unless they're in a molten or a liquid or a solution state. Why? Because in a solid state, the ions are not free to move. That's what I told you. They are packed in their position, and the maximum they can do is that they can vibrate around their place. That's it. So you need to have them in voltage state, or you need to have them in aqueous state. So um you can go ahead and you can uh, uh, have the ions free. So the ions are free and they're able to conduct electricity. So that is what we know about their electrical conductivity. That's it for the topic of your ionic bonding. Now let's move on to the next type of bonding that we need to know, and that is our metallic bond. Just give me 1 second.
Can I ask you a question before
Yeah,
we?
go. Yeah, go ahead. Go ahead.
What about heat conductivity? Do they conduct heat in solid state?
They're not very good conductors of heat.
Okay.
Once again, when you're talking about conduction of heat, so generally, once again, if they are in a solution or a molten state, they are generally able to conduct heat because the ions can move around. But in solid state, that is the problem, that it is not going to happen. Why? For that, you need to go back to your kinetic theory of matter, right? So when you talk about your kinetic theory of matter, in kinetic theory of matter, your the theory states that the heat is transferred by the collision of particles. So the particles are going to collide with each other, and that transfers the kinetic energy from one to another, right? So whenever you're heating something up, what happens? The molecules gain kinetic energy and they start moving faster and faster. So for conduction of heat, the particles have to be free to move. So once again, an ionic solid is generally solid, is not going to be capable of conducting heat, is not going to be that good because ions are in their fixed position. In solid, in liquid or in a molten state or in a solution state, they are going to be able to conduct electricity because now they are free to move. So they can, when you apply heat to them, they can gain kinetic energy, they can move around, and they can, when they bump into each other, they can transfer that energy to the other ions as well. All right, does that answer your question?
Yes.
Okay, hold on 1 second. Let me just share metallic bonding with you. Open that. All right, so let's go on and talk about metallic bonding, right? So metallic bonding, what is metallic bonding? First, before we get into that, we need to understand the structure of metals. In the structure of metals, what do we have? We have these positive ions, and those positive ions are surrounded by a sea of delocalized electrons or a sea of free electrons. Now, what happens is that metallic bonding is the electrostatic force of attraction between the positive ion and the free electron. So the electrostatic force of attraction, that force of attraction is the same, it's electrostatic. Electrostatic force of attraction between the positive ion and the free electron, that is basically going to be your metallic bonding. Metallic bonding is present inside your metals. So you have group 1 metals, group 2 metals, and you have your transition elements. Now, we already know that metals are good conductors of electricity. Why are they good conductors of electricity? Because the electrons are free, they're delocalized, they're easily able to move. So whenever we will apply voltage, whenever we will apply electrical power or voltage on a piece of metal, what will happen? The negative terminal of the battery will repel the electrons. The positive terminal of the battery will attract the electrons, and the electrons will start to move from negative all the way to positive. So because these electrons are free to move, they can go from negative to positive. That is why metals are generally said to be good conductors of electricity. Now, what other properties of metals do we know? Can you let me know if you know any other properties of metal? We know that they're good conductors of electricity. Do we know any other?
Yes. Okay. Firstly, they're good conductors of electricity, as you just said, and heat as well.
Mm-hmm.
Secondly, they're malleable and
Yeah,
ductile as well.
yeah, yeah.
They also, I think, I forgot the rest. But also, I have a question just before we move on to
Go on, go on.
questions. So you said metallic bonding is the electrostatic force of attraction between the electron and the proton.
Exactly.
But
Don't
isn't
say proton. Don't say proton, say positive ion. Proton is present inside the nucleus. It is the positive ion that is present.
okay, but isn't this the same thing as the ionic bonding? Because
Ionic bonding is between two ions. Electron is not an ion. An ion is an atom that has gained or lost electron, right? An ion is still an atom. You still have a nucleus that is surrounded by electrons. That is a proper atom. The only difference is that it has gained or lost electrons. That's it. That's it. But it is still an atom. It still has protons, neutrons, and electrons. Ionic bonding is between a positive ion and a negative ion. Metallic bonding is between an ion and an electron. That is between two ions. Both the ions are still atoms. They will have the entire structure. Over here, the positive ion is the atom, but the other one is just a single electron. There is no nucleus, no nothing. So it is different than ionic bonding. Ionic bonding is between two ions. Metallic bonding is between one positive ion and just one single electron or as many electrons around it. Is that making sense?
yes, kind of.
And
And
it's yeah.
sorry, go on.
It's basically what is happening is that in an ionic compound, you have literally an ion. So for example, I have sodium chloride, right? I will have the nucleus, I will have the shells, I will have the electrons inside the shells, right? So this has a positive charge, and this is chlorine with the negative charge. Now, both of these have a nucleus in the middle. Both of them have protons, both of them have neutrons, and both of them have the entire atomic structure. So the force between these two, between positive and negative ion, very specifically ion, is ionic bonding. In metallic bonding, you have just one ion, right? This ion, for example, is present like this. Now, there are no other ions. You don't have a negative ion present. There is no negative ion. You only have a positive ion and a simple electron. This electron does not have protons. This electron does not have neutrons. This electron is not an ion. An ion is an atom. An atom can turn into ion, right? This is just an electron. That's it. So the force you have between the negative electron and the positive ion, that is metallic bonding. In metallic bonding, you will have same type of ions throughout. If it's sodium metal, it will only have sodium atoms. In an ionic compound, you have two different ions. You will have sodium or chlorine, magnesium oxide, right? You will have your lithium nitride, so lithium and nitrogen. You will always have two, a metal and a non-metal, and both of them will be ions, which means they will be complete atoms. They will have protons, they will have neutrons, they will have a whole atomic structure. In metallic bonding, all of the positive ions will be of the same metal, right? Unless you're making an alloy, which I will get to, but all of them will have the same elements: nitrogen, 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 nitrogen. Sorry, I'm saying nitrogen, sodium, 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 sodium. And the next one, the negative one, will just be a simple electron. It will not be an ion. It's not going to be an atomic structure. It's just going to be a small piece of it, that is electron. So the force of attraction between them is your metallic bond. Is that making sense now?
Yes, and also the other question is, last class in the physics class I took with you, you said that current flows from positive to negative.
Okay. So when we are talking about it, you have two types of current. Okay. You have conventional current, and you have the actual real current. So in conventional current, what happens was that a long time ago, when the scientists were first studying electricity, they used to believe that the electrical current is flow of positive ions. So they used to say, I'll just try. So they used to say that the electrical current is going to travel from positive to negative. Now, these days, you and I know very clearly that the current is not positive ions, the current is negative ions. It is the flow of electrons. But when to this day, uh, when you are dealing with physics past papers, you will see two types of. You will see them say, tell us the direction of conventional current. This is conventional current. Even though we now know that it's not positive ions, it is the electrons that are flowing. Since this had already become a standard, the scientists stuck with it. So whenever you're talking about conventional current, we always draw it as positive to negative. In your past papers, there are literally questions where they say, draw the direction of conventional current, draw the direction of electron movement. They like literally differentiate it. So electrons are moving from negative to positive. That is how electrons move. They are moving from negative to positive, and your current is the flow of negative electrons. But since positive to negative had already become standard and widely accepted, it stayed behind and they named it conventional current. That this is the conventional traditional current, and then you have the actual flow of electrons, which is negative to positive. So whenever they ask you conventional current, you always show from positive to negative. So there are literally questions in past papers where they have like part one, draw conventional current, part two, show the movement of electrons. The movement of electrons is actually in reality Current is from negative to positive. But since it had already become a standard and widely accepted, so they stuck with positive to negative. That is known as conventional current. Is that making sense?
Yes.
Okay. So this is what your what you know about your electricity. Hold on 1 second. Let me open one more thing for you. Okay. Now, talking about malleability and ductility, what can you tell me about that? First of all, what do we mean by that? Malleable and ductile.
So malleable is basically being able to hammer it to sheets without it being brittle or breaking apart.
Yeah.
And ductile is basically being able to form it into strings or wires without it
Yeah.
breaking.
Wires is better. We're not going to say strings. We are going to say that it's going to be wires. Good job. Now, why are they malleable and ductile? Do you know the reasoning behind it?
I think it has to do something with their structure.
Yeah, it has something to do with the structure. Let me just show you 1 second.
Is it because of their outer shell is not full of electrons?
I'll tell you. So, when we are talking about it, 1 minute. Okay. Okay. This is why. Because what happens is that when we apply any force, right? So malleable means that you can hammer it into different shape. Literally, when you like watch movies and you see that, oh, they're making a sword, right? So you often see that they're hitting it with a hammer. So that is why, because when you hammer it, when you apply the force, you can turn it into a different shape. Now, when we are talking about a different shape, what is actually happening? What happens is that when you apply the force, the layers are able to slide over each other. Just like in ionic compound, the layers are able to slide over each other. But the problem in ionic compound was that the same charges would come on top of each other and that would create repulsion. But in metallic bonding, that is not a why? Because the electrons are free to move. So if you end up getting an electron on top of an electron, they can simply move away. Or if you end up getting positive ion on top of a positive ion, an electron can come in the middle and take away the repulsion. So in ionic compound, they are fixed in their position, they cannot move. So when they slide over each other and they end up coming on top of each other, chlorine on top of chlorine, sodium on top of sodium, they end up getting repulsion and they end up breaking. But in metallic bonding, when they slide, the electrons are free to move. So electrons are free to move, and wherever there is going to be repulsion, electrons can just move accordingly. So the layers are able to slide over each other without any repulsion. So that is why you can literally apply force and change them into any shape that you want. Is that making sense?
Yes.
Now, when I am talking to you about properties of metals, these are the properties of metals that you can go ahead and learn in comparison to non-metals. So metals have high melting and high boiling point. Why do they have high melting and high boiling point? Because they have that electrostatic force of attraction. Each positive ion is attracted to the electron. Positive ions are attracted to the electrons. They have strong bonding between them. That is why you need a lot of energy to be able to break that bond. You need a lot of energy to be able to break them away from each other. So that is why they have high melting point and high boiling point. And they also have high density. They're really dense, right? They're really dense because they're very closely packed to each other. They're really closely packed with each other. Non-metals, on the other hand, they will have low melting point and low boiling point. Metals are shiny, non-metals are dull. Metals are malleable and ductile. Non-metals are brittle. Non-metals are brittle, just like ionic compounds, they're brittle. They break very easily. And non-metals cannot conduct electricity. Metals can conduct electricity and heat as well. And non-metals can make both. They can make ionic compounds as well and covalent compounds as well. So non-metals can make more. They can make ionic bonds and covalent bonds. Metals can only make ionic compounds. That is it. Non-metals will generally, they are going to be the negative ions. So if you have an ionic compound, the non-metals are always the negative ion. And metals are always going to make the positive ion. So that is the major difference that you have to do between them. Any confusion in that?
Yes. Is metallic bonding the same thing as covalent bonding? It isn't, right?
No. Metallic bonding is the bonding that is present in your metal. Covalent bonding is the bonding that you have between two non-metals. Metallic bonding is the bonding inside that metal. If I take a piece of sodium or I take a piece of copper, the bonding inside that copper is metallic bonding. If I take that copper and I react it with chlorine, for example, copper chloride, if I make it, if I take that copper and I add chlorine to it, that becomes ionic bonding. So copper on its own will have metallic bonding, like just a piece of copper. It has metallic bonding inside of it. I take that piece of copper and I combine it with a negative ion like chlorine, that will become ionic bonding. Now, what if I have two non-metals like oxygen? You know the formula of oxygen is O2, right? Why? Because two atoms of oxygen are bonded to each other. So oxygen is non-metal. So when non-metals are going to make bonds with each other, that is going to be covalent bond. So they are completely different from each other. Metallic bonding is present strictly in metals and not in any other compound. Your metallic bonding is literally going to have the metallic bonding inside, like just a piece of metal on its own will have metallic. If you combine that piece of metal with a non-metal, you end up with ionic bonding. And if you combine two non-metals with each other, you get covalent bonding. Is that making sense?
Yes.
Okay. Now, another thing I want to ask you, do you know what is an alloy?
Yes.
What is an alloy?
It's a mixture of metals.
It's a mixture of two or more metals or a metal with a non-metal. Both options are there, right? You can have two or more metals or a metal and a non-metal. They can also be used to make a alloy. Now, when we are talking about it, uh, alloys are stronger than pure metals. Do you know why alloys are stronger than pure metals?
Yes, because they have properties of different metals and different elements.
Okay, fine, that's true. They do have different properties. Main reason is this. So let's say you have two metals, right? And you've mixed them together. So, for example, this is copper and this is iron, for example, and inside it you have mixed copper. Now, iron is a different size and copper is a different size. So what is going to happen? You're going to have
They're going to be closer to each other.
yeah, basically no. What's going to happen is that in an alloy, if you have two different metals, so the ions or the particles have different sizes. Since the particles have different sizes, so now what's going to happen is that whenever I'm going to apply force, the layers will not be able to slide over each other because they're all different sizes, right? So if I try to apply a force, they can't slide over each other because they're of different sizes. Since they can't slide over each other, that is what makes them really, really strong. So even if you hit them, even if you hammer them, they generally do not change their shape or they don't get dented easily. Think about an armor, right? You're sending someone off to battle and you've given them an armor. Now, you would want that armor to be strong, right? No matter what blows they're getting, whoever is hitting them, we want that armor to stay in its place. We don't want it to bend. We don't want it to, break down. So that is where an alloy would come in handy. Alloy would make sure that whenever a force is applied, they're not going to be able to slide over each other. They will not be able to slide over each other, so it's going to retain its original shape. Or when you are, making protective gear like helmets and stuff, you will want to make sure you make it of a hard enough material that it is able to resist bending. We don't want it to bend because if a helmet is going to bend, it's going to bend inside your skull, right? We don't want it to bend. We want it to stay as it is. So in that situation, you would choose an alloy. The layers will not be able to slide over each other and they will retain their shape. Is that making sense?
Yes. So are they stronger than ionic compounds?
And alloy is stronger than organic compound. You can't really compare them. I mean,
Okay.
metals are generally better than ionic compounds in the way that it's not about strength, right? It's not about them being strength. It's about the fact that your metals are simply able to slide over each other. That is why they don't break easily. Like they will change their shape, but they're not going to break apart. Ionic compounds, on the other hand, they will break apart. Now, if we talk about bond strength is a completely different. When you talk about alloy, you can compare an alloy to a metal, but you can't compare it to an ionic compound because ionic compound is completely different.
Okay, what about a metallic bonding compound?
So you are going so whether it's an alloy or whether it's a pure metal, you will have metallic bonding. The strength of it has nothing to do with a metallic bond, right? The strength of it has to do with how many metals you have. So over here, the strength has to do with you mixing two or more metals. So the layers are not able to slide over each other, so they can't change their shape, right? It doesn't have anything to do with the strength of metallic bond. Metallic bond is not like it's not between two atoms, right? It's just one atom. You just have sodium atoms throughout. That's it. Even now, when you have an alloy, this, for example, this is aluminium or this is iron and this is copper. The iron and copper are not bonded to each other. Let me be very clear. They're not bonded to each other. Why? Because they're not giving electrons to each other. They are not sharing electrons with each other. They are not making a bond between them. It's just mixed in. It's like you have taken sand and mixed a pink color powder in it. They're both present over there. They're not bonded to each other. Just like that, copper and iron would not be bonded to each other. They are just going to be present right there next to each other. Their bond is going to be with the electron. This copper will also be bonding with the electrons, and the iron will also be bonding with the electrons. That is metallic bond. They are not going to have any sort of bond with each other. So you can't really compare it to an ionic compound or a covalent compound. Ionic compounds between two other compounds. This is just inside one compound. Is that making sense?
Yes, but I'm still confused in the metallic bonding as to where we get the extra electrons from.
The extra electrons are coming from this. This is your positive ion. For example, you have a copper ion, right? So why is it an ion? Because it has less electrons. That is what a positive ion is, right? In positive ion, you have your less electrons. That is what is it? More protons than electrons. This is where it is coming from. One of the electrons has escaped from the atom of copper and it is now free. That is where your free electrons are coming from. These positive ions, where did they come from? They lost some electrons, right? That's how they became positive. So when the lost electrons, where did they go? They became free electrons.
Okay, so can I just ask you a kind of
Mhm.
complicated question? It's a long question. So
Mhm.
basically, metallic bonding happens in one element only, like it takes place in one metal.
Yeah.
And it's basically the forces between the electrons and the positive ion.
Yeah.
Okay, so it only happens with positive ions, meaning only group 1, 2,
Yeah.
and
Yeah.
3, right?
Yeah. Exactly.
And basically what happens is that they need to lose electrons to maintain a full outer shell.
Yeah, exactly.
So where does the bonding come from again?
So, okay. To be clear, in metallic bonding, you don't have two ions combining with each other, right? You just have one ion, and that ion has a positive charge. And since that has a positive charge, it will have an attraction with the negative electron. That is the metallic bond. Don't think of metallic bond like an ionic bond that is present between two things. So then you have to break it apart, you have to separate the two ions, right? That's what we did in electrolysis, that if we have sodium fluoride, that's an ionic compound. We have to break them apart from each other. That's not true for metallic bonding. Metallic bonding is just a piece of metal, and inside that metal, you have positive ions and you have electrons. And in that the attraction between the positive ions and the electrons is known as metallic bonding. That's it. It's not between two compounds. You can't take away the positive ion and you can't take away the electrons. You can't break it apart. That is why when you're applying force, the layers are just sliding over each other. That's it. Because there are no two compounds. You just have one positive ion, a bunch of electrons, and the attraction between them is your metallic bonding. That's it. So it's not between two metals or two structures. It's not typical traditional bonding. Don't think of it as like bonding. Think of it like metallic structure. That's it. And even forget the term bonding. The term bonding is a bit confusing. It's just metallic structure. This is the structure of metal. That you have these positive ions and you have the electrons, and the positive ions and the electrons are attracted towards each other. That's it. In ionic bonding, in covalent bonding, you always have two atoms, two ions, two atoms that are going to be attracted over here. In metallic bonding is just metallic structure. That's it.
It's
And
basically
yeah, it's just the normal structure of metals. That's it. We say metallic bonding, but it's not like you are joining two metals to each other and the bond between them is metallic bonding. No, metallic bonding is just a way of saying metallic structure. That's it.
okay, so it's basically just the intermolecular forces between
Yes,
the nucleus and
exactly.
the
Oh, no,
electrons.
you can't say intermolecular. Intermolecular is a different term. Intermolecular is when you have molecules. Molecules, what are molecules? When two or more atoms will combine with each other. For example, two chlorine will combine each other to make Cl2. That is the molecule. Over here, you have ion, positive ion and an electron. So just the force between them, or just the attraction between them, is your metallic structure. That's it.
Okay.
If you
And
say intermolecular, you're going to lose marks for that. Let me be clear, you're going to lose marks for that because intermolecular is between molecules. Molecules are covalent compounds, so that is going to be something different.
okay, now I get it. I finally get it. And it doesn't have to have a full electron shell, right? It
No,
doesn't.
no, nothing, no. You don't, yeah, because no full electron shell, nothing like that. It is simply that you have just the metal ions are there, and the metal ions have lost some electrons. So they're surrounded by free electrons, and this is the normal structure of metals. So metallic bonding is just a way of saying metallic structure. That's it. It's not typical traditional bonding where you have two compounds or two ions or two atoms, and then you're joining them to each other. No one is joining with anything. It is just normal metal structure. You have positive ions, you have electrons, they're attracted to each other. That's the normal structure of metal. And this attraction is what we call metallic bonding. It's not traditional typical bonding.
Okay, now I finally understand. And one last question about electron configuration.
Yeah, go on.
As to shells, firstly, what's the maximum number of shells an atom can have?
Okay, so if you're going to, for example, go ahead and look at your periodic table. So in your periodic table, if you take a look at it, right, this is your periodic table. So the period number will tell you the number of shells. So we have 7 periods. So 7 is the maximum number of shells it can have. So
Okay.
period number 1 means it only has 1 shell. Period number 2, all the elements that are in period number 2, they have 2 shells. Period number 3, they have 3 shells. So you go all the way to 7. So 7 is the maximum number of shells you can have.
Okay, and what's the maximum capacity of one shell? I know for the first 3 shells, it's 288, and then what?
Okay, so that is something that I don't want to get into because that is something that when you're doing your A levels, you're going to have to get into it, but it increases. It gets up to 18 and then it gets up to more and more and more. So when you're talking about the maximum capacity for your level 288 is fine. You don't need to get into more than that because then that is going to be A level syllabus. That's the entire topics in your A level.
Okay.
Yeah, because okay, just to give you a small hint, so in you just know your shell, right? Shell number 1, 2, 3. In each shell, you have even smaller shells that we call suborbitals. And then each shell has its own subshell has its own capacity. So that is a really huge topic. So depending upon what subshell is present, the capacity changes.
Okay.
Yeah, so that's like a whole lot of unnecessary details that's just going to confuse you. That's it.
Okay, thank you.
Okay, all right. So we're just going to stop it over here for today, I think. And then in the next class, we're going to go ahead. First, we'll do a couple of questions related to ionic bonding and metallic bonding. And then we'll go ahead and start with the actual topic of covalent bonding. Okay?
Okay, sounds good.
Okay. All right. Thank you
So
so much,
much.
Dana. Let's see you in the next class. Have a good day.
Have a good night, you too. Thank
Bye,
you.
Dana.
Sorry
Bye.
for my questions.
No,
They're
no,
kind of
no
confusing.
problem. No, you can